some students use WebAssign for messaging. Don't do that. I don't treat them because of simple reason. WebAssign does not notify me, and it might take days, weeks before I notice that someone left a message. Messaging board for our course is Piazza because as long as you leave a message there, I immediately get an email that someone left a note. That's it. This is the problem we have solved yesterday. That's literally the last slide we saw, and there was a question about what happened to work. Well, again, we need to remember this problem has two different sub-problems. One, we call it collision. Second, we call pendulum. Yeah. So here, friction is involved. When pendulum swings up, there is no friction. We neglect it, and theoretically, that could have been a good question. I will ask it later officially, but theoretically we could talk about also work done by force of tension. However, good thing about tension, it doesn't do any work. Same way like normal force doesn't do work, by same reason. During the motion, the force of tension remains perpendicular to the motion. Cosine of 90 is 0. So the only work done here is gravity. So gravity does negative work on its way up. But here, to keep the ball inside of the pendulum, friction is involved. And again, just to refresh how do we go about it, we need to compare energies, and that's what the missing part. So a bullet had certain kinetic energy, mass, speed squared over 2. The pendulum wasn't moving. That's the initial kinetic. Which is the same as or just and right after the bullet stuck and they start moving away, we know we have solved of the velocity. They start traveling at 1 meters per second together, and new mass is 0.99 plus 0.01 is 1 kilogram. The new speed is this. So that will be final. Final for what? Final for the process we call collision, but the same energy becomes the initial for the process we call swinging. So, and you can see clearly different numbers. 0.5 joules, and here 50 joules. So that's how much negative work friction did to stop and to hold the ball inside it. Any questions? If we talk about type of a collision, we always compare energies. And if energy doesn't change, that's what we call elastic or absolutely elastic collision. If it changes, but due to friction, but objects travel separately, that's regular inelastic collision. And if they travel together, that's absolutely inelastic collision. Well, the last situation to discuss is a two-dimensional collision. And All right, this is dead. Well, anyway, I can manage. Something like this. Now, it will come back to you every night now, in your dreams. Don't scream. It's not gonna help. Now, the only difference between situation happening in two-dimensional, flat surface or plane, and one-dimensional is that now we have to treat vectors indeed as vectors. And we know that we have two options. We can use components or we can use triangles. And there's a specific example. What we have, two objects collide, in this specific example, at 90 degrees to each other. And after the collision, they travel together. So what is the name of this collision? Yeah, completely or absolutely inelastic. So they stick to each other right here, and they travel together. That's it. So these are velocities. And that's what we're looking for. The law, people sometimes forget that the law doesn't relate velocities. The law relates momentum before and after. So we need an arrow which represents the initial momentum of the first object before the collision. That's supposed to be mass times velocity. Well, we can write a number, and that points to the right. That's P1 initial. The arrow represents the direction. And the P2 initial should be equal to the big M, which is twice of the little m, times the speed, and that should point down. And this momentum, P final, should be equal to total mass, which is the sum, times, well, wherever it is, we don't know. And it should point a certain direction like this. In this situation, the equation P1 initial plus P2 initial should be equal to P final. At this point, you have to make a decision for yourself. Do you want to use components or do you want to use a triangle? I want to use a triangle because when direction is perpendicular, I expect to have a right triangle in the end. So this arrow plus this arrow, they together should give me this arrow. This arrow is 3 times m, which is the mass, long. This arrow is 4 times m. This arrow is supposed to be equal to 3m times v, units long. What is the unit of momentum? Actually, I didn't say, but it has no special unit. It's just kilogram times a meter divided by a second. And since this is a 90 degrees angle, the relationship between hypotenuse and other sides is given by the Pythagorean theorem, which means this should be equal to square root of this plus this. This is that unknown velocity which we need to calculate. And so please tell me. At this point, again, physics was done. Geometry is done. Arithmetics, how do you spell? Gives the number. So please, anyone? That is not a number. For velocity, for v, for this variable, we should get just a number, even if we don't know the actual mass. That's again an example when we don't really need to know something. What we know is the relationship between these two masses, and that's completely sufficient here. So what is the number? 5/3. That's it. It's a 3, 4, 5 triangle divided by, so 5/3, 5/3. Of course, you could have used components. You would get exactly the same result, of course, in the end. And when people use components or vectors in a situation like that, they often stuck on the fact that the mass is not given. They say, I don't know the mass, so what? Just go ahead and act in exactly the same way you would be acting if you knew the mass, and just believe it will be canceled. And the stronger you believe. Any questions? Because we are almost done with this topic. Now we're going to talk about center of mass. It's a specific abstract point. We talk about it when a system is large, but we actually don't care about how individual parts of that system might move. All we care about the system as a whole, like airplane. We don't care if its tail or cabin move separately. They don't, because that would have been very, very bad. So we just treat it as a point flying in space. And that point actually, specific point which we can use to describe the motion as a whole, that point has this name, center of mass. So if you look at something large and move away from it, relative to you, it starts looking smaller and smaller and smaller. And if you're far enough, you don't see the details anymore. You just see one little dot. That little dot represents the same system with the total mass of the same system. But it will be moving like a ball. So I'm going to throw this. This is a system. It has some size, but the center of mass of this system should be moving exactly like a standard ball moves. This is supposed to be the trajectory of the center of mass of this system. Come on, come back. It's just easier to see for your next nightmare. So most probably I can do it only once because when it falls in the ground, it usually breaks. So watch closely. This light should travel like a regular projectile. So now next time when you hear this word center of mass, well, actually it's still working. Let's see how many times should I drop it before it breaks. I made it. It's never gonna break. All right. Since we can apply the same equations we've applied to a single ball to the whole system, we can write the Newton's law for the whole system. It should be the net force equal to mass times acceleration. This should be the total mass of the system. And that is the acceleration of that abstract point, acceleration of the center of mass. What forces should we include? Well, when we talk about the system, there are two types of forces: internal, between the parts of the system, and external, from the outside. And internal forces don't affect its motion. There is no self-action in physics. It's only in our mind we can propel ourselves to the next level. But in physics, there is no self-actions. The objects cannot act on themselves. Newton's first law says if you give a ball a toss and nothing acting, it will travel with constant velocity forever. Bless you. And in particular case, when net force is zero, acceleration should be constant. If zero, if acceleration zero, velocity is constant, momentum of the system is constant. This is another approach to the law of conservation of linear momentum. When all forces acting on a system from outside cancel each other out, the total momentum of a system conserved. But more important fact is when velocity remains constant, if system was at rest, after that, no matter what's happening, the center of mass of the system should remain at rest, even if the parts of the system move relative to each other. So these are the equations which we could use to calculate the actual location. So for two objects, the center of mass is closer to the heavy. For three objects, again, the center of mass is closer to the heaviest, farther for the light ones. And this is a standard problem. You can look it up. What is happening to the center of mass when the system was at rest initially? But then, like in this problem, person walks, what should happen to the boat? Well, we have a situation very similar to it. First, let's see what's going to happen if I hold it. Not surprising at all. It's like traveling on the ground, right? So in this situation, if I look at the cart as a system, of course, the center of mass is close to this weight. It's 1 kilogram. And that center of mass was traveling. Why? Because friction between wheels and track was propelling it ahead. What's going to happen if I let the track off? Why would it travel back? Because when now the system is composed of these two objects, what's this for? To eliminate friction. So external forces would have been friction, gravity, and normal, but gravity and normal cancel. Friction is zero, which means the center of mass of this system, track and cart, should remain at rest. So when this cart was traveling to the right, to compensate that motion, this start traveling to the left. And if we calculate the center of mass of the system of these two objects, that actually wasn't moving at all. They're all alive, in a way. So now we start a new topic, circular motion. What do you think is an official definition of a circular motion? Exactly. What is a circle? Next natural question. Anybody? What is a circle? We know it's not a triangle, it's not a square. We know the difference, but actually there is an official definition in geometry for a circle, a parabola, a hyperbola, and all shapes. What do you think is a circle? What do we call a circle? Exactly, that's an official definition. A circle is a line or a set of dots which located all at the same distance from a given point. That given point we call a center, distance we call radius, and that's what we call circumference. That's it. And there are different types of vertical motion, circular motion, vertical like this, horizontal like this, and physics is practically the same for all of them. I want to ask you this question. Imagine that, well, relative to you, that looks like a vertical motion, yeah, but it might have been a picture from the top looking at a person and making a horizontal circular motion. Doesn't matter. So if this, at this instant, the string would break, how would the ball travel afterwards? This is the question. What trajectory do you think should we choose for the ball? And we know an answer because we know in general that velocity, instantaneous velocity, always points in a certain way. For any type of the motion, not just circular, for any type of a motion, instantaneous velocity always what? Please finish this sentence for me. Anyone, yes? Tangent, exactly. And if object after being released has instantaneous velocity in a certain direction, it will be traveling in the same direction until gravity or something else start affecting it. So here, the trajectory is number 2. Yep, it's not a tricky question, it's just a review. What do we know about instantaneous velocity? And in a fraction of a second, the ball will be at a different location. That means the instantaneous velocity also changes, right? It's important to remember. We have 2 situations to discuss. First, a motion, a circular motion with a constant speed has a name, uniform circular motion. This word, uniform circular motion, means the speed remains constant. So we don't speed it up, slow it down. It travels same distance over same time. And a general situation when speed changes, in that situation we have no name. It's just a general circular motion. For the uniform circular motion, what would you say? Is that not a question to answer on a web assignment? Just tell me, what do you think? If velocity is constant and not equal to 0, first of all, would it be circular motion? If velocity is constant, what do you think? Would it be a circular motion? No, parabolic, rhomboidal. All right. Can it be all of the above? Can it be none of the above? Technically, could be, but the right answer is what? No, we're going to talk about circular motion, but we need to see the difference between circular motion and a linear motion. No, and correct answer to this question is linear. That's Newton's first law, which we've studied 2 weeks ago. Still works, same law. When velocity remains constant and not zero, object travels straight ahead until something starts affected. But in this situation, we don't talk about velocity. Those vertical bars, what do they mean? Magnitude, that's speed. So when we talk about motions, we have to be very careful with words, especially when we talk about circular motion. Speed and velocity, very different things here. Now, my next question. So I want to show you what is happening. I have a very expensive demonstration prepared for you. Memorize the vision of this. And now, please answer the question. In this particular experiment, a small object was attached to a string, was moving in a circle on a table. And that's something I want to see. Oops. So these are the answers. Question number 3. Who said cold? Probably a sign of being nervous and pressing wrong button. Relax, it's Friday. Friday, for Russians, is like a little Saturday. So, 50-50, almost 50-50. All right. That will mess up my numbering. I will ask the same question again. What I want to do now is copy this picture, please, and draw a free body diagram. Now, when we talk about circular motion, it's very important to be able to look at the situation from 2 different perspectives. This is what you saw through the camera. Yeah? This picture represents a snapshot. That's what we call a top view. But also, for many reasons, it's also useful to imagine the side view. What would you see if you would be looking at it like this? Depending on the view, some forces become clearer than others. And for the top view, this is the center, this is the string, this is the object. Unfortunately, I cannot use top view to show clearly gravity and normal, because they're supposed to kind of move away from our eyes or toward our eyes. We'll talk about it later. But what I want to do to see those forces, I want to imagine that I'm turning this view. What do I see? I see a string. I see an object. And now I can see same force of tension, normal force, force of gravity. Theoretically, if it's been moving, let's say, counterclockwise, there's supposed to be also the force of friction between, but it doesn't matter. So you should have your own diagram. And now what I have to do, make it question 4, and ask you again, what do you think? And don't say cold now. This is probably the most important point of this whole topic. You have to choose between acceleration is 0 and acceleration is not 0. So now it's going to be question 4. And if we draw a free body diagram, that completely messes up my numbering. If we draw a free body diagram, what law do we use after drawing a free body diagram? That is correct. And what is the name of that law? So Newton's second law says that net force should be equal to m times a. So we have two options. 0, hence acceleration is 0, or not 0, hence acceleration is not 0. Now, look up at your free body diagrams one more time, write the law, and now it's going to be question 5. We've got all weekend ahead. So, 5. And resend. And he's still collecting your answers, so it's going to take some time. One more time. Still working. One more time. Okay. Now we can move on. We couldn't move on until we get the distribution which is supposed to demonstrate our knowledge of how second Newton's law works, because we've studied it before the exam. This is how it works. If net force is 0, acceleration is 0. If net force is not 0, the acceleration is not 0. And net force acting on this object cannot be 0. For example, nothing compensates tension. Gravity and normal, well, yeah. Friction might be neglected, but nothing compensates tension. Tension is the reason it doesn't fly away. We cut the string, it flies away. So when object makes circular motion, acceleration just can't be 0. It is never 0 for a circular motion. Well, of course, the question is, how can we calculate it? And we have two approaches. First comes from the past, Newton's second law. And this doesn't have to be tension every time. It could have been any force which makes an object move in a circle. Force of gravity makes satellites orbiting the Earth. If you're on a roller coaster, that's normal force, which curves your trajectory. So the nature of that force doesn't matter. But we also can do some geometry. This is a copy from textbook. You can read that page. Another fact about this type of acceleration, it always points toward the center of a circle, and the magnitude equals speed squared divided by radius. You can just do that little geometry, because delta V over delta T is acceleration, but v is vector. That's important to remember, because velocity changes even if speed remains constant. Speed is the magnitude of velocity. So each velocity arrow has exactly the same length, but at different locations it has different direction, because it always has to be tangent to trajectory. That's why velocity changes, and that's why acceleration can't be zero, because change in the velocity is never zero. And if you do some mathematics, instead of delta v over delta t, you get v squared over r. Yes? Again, we talk about a specific case which has a name uniform circular motion, which means speed remains constant, and in that situation, the acceleration always points to the center. Well, first of all, the acceleration equals delta v over delta t. So acceleration always points like delta v points. And delta v, see this vector, points to the center. Well, not exactly when we choose two locations far away from each other, but if we make them closer and closer and closer and closer, this direction becomes direction at the center. And if the ball is here, the acceleration points still at the center. If the ball is here, the acceleration points at the center. For a uniform circular motion, the acceleration always points to the center. So this is everything you need to remember for acceleration. It has a name, centripetal acceleration. So if you hear or read it, it means this is the magnitude of it, and the direction is to the center. If velocity changes, that changes things a little, but so far we only talk about a uniform circular motion. Now, that's it. You know everything you need to know to solve any additional problem. This is not a new stuff. As long as forces acting on an object, we always can write Newton's second law. But when that object travels in a circle and speed remains constant, we can also add an expression for the acceleration. That should be this. And we know that it should point to the center. So starting from this second, you can do this homework, which means homework 2 part 1 and homework 2 part 2 should have been finished already. And people sometimes use this term, centripetal force. Well, it's a term. It's not like actual force. There is force of tension, gravity, elastic, normal. Those are of friction. Those are forces, actual forces due to the interaction. The centripetal force is just a term. It represents a product, mv squared over r. That's it. So if you hear or read it, that means this number, a combination of mass times speed squared divided by the radius. But it's not an actual force. It also represents, due to Newton's law, the net force acting on that object which travels in a circle. Just a term. Now, we're going to talk about two types, vertical and horizontal circular motion. Start from vertical. It describes many important practical situations. Stunt pilot making a large circle in the air, a ball on a string, roller coasters, a car travels up or down the hill. Those are all complete circular motions or parts of a circular motion. For the vertical circular motion, we have two special cases, and only two special cases we should be considering: the lowest point and the highest point. So please follow me, draw a free body diagram for the lowest point. This is what we always can imagine. So a ball, we take a photograph, a snapshot when the ball travels through the lowest point. Travels through, right? So it is moving. It's not at rest. How do we describe this fact? Well, we can show a velocity. Velocity points, let's say, to the right. Now, at this very instant, how many forces are acting on the ball? What do you think? Gravity and tension, of course, nothing tricky about it. How does gravity point? It always points down. And tension points along the string. Now, this is the center of this circle. The centripetal acceleration is supposed to be pointing at the center of the circle. Technically, it is not a uniform circular motion because on its way down, the object is kind of speeding up, on its way up, slowing down. But at the lowest point, that doesn't matter. We can see that at this point, everything is vertical. So the equation is very simple. M times A should be equal to tension minus gravity. Why do I subtract mg? Points opposite. So since we know the magnitude of the acceleration equals mv squared over r, that's how we can write the equation. And normally people would ask, what will be the tension equal to at the lowest location? And we would say this. And if you've been on a roller coaster or just on a swing, you feel like heavier at the bottom. It presses you into the seat. That's why. This is what, again, we used to call, if instead of a string we would have like a spring scale which measure force, we would call it the magnitude of the apparent weight. Apparent weight, it should be AW, not WA. Apparent weight. And every string, every structure has certain limits. For example, if you pull on a string too strong, it might break. So, or the roller coaster, you know. So people need to calculate this number and compare to that limit it's capable to sustain. If you start moving faster and faster, you're increasing apparent weight or tension, and it might break. Now at the top. So please draw a free body diagram and show very clearly the acceleration for the object at the top. And then please take a very, very, very smart phone, take a picture and send it to me. It's going to keep me busy over the weekend. So again, we always can imagine a ball traveling in a circle, and we take a photograph at that moment when the ball is at the highest location. Just checking if all the signs still working, and the next question will be 6, if it will be the next question. Of course, our ultimate goal, again, is to calculate apparent weight or tension. Could have been normal force, if it's a rail. You know. So, force of gravity, how does it point? Okay. Before I start getting pictures or emails, I can draw mine. Oh, that's my. Come on. Okay. So force of gravity, always down. What about tension? How does it point? Down, because the string pulls it in down. So tension. What about centripetal acceleration? How does that point? So that's it. And we could have choose positive x direction down because everything points down, but let's stick to our choice. In that case, we should write m. Everything is negative, times is -1, everything becomes positive. So mv squared over r should be equal to tension plus gravity. So tension, or apparent weight, should be equal to mv squared over r minus force of gravity. R represents the radius V represents that instantaneous speed, which is different technically at the bottom and at the top for the ball. However, if you ever saw a motorcycle stuntman, because he can manage how fast he travels, and there's some friction, he actually can manage making uniform circular motion. So the speed would be exactly the same. It doesn't matter for these two specific locations. For these two specific locations, we always get these two specific equations. That's it. And then again, the nature of that force does not matter. Tension, normal, gravity, electric, whatever. Doesn't affect equations. So this is an experiment which every lecturer likes doing. Here. So a cup, well, a ball, what's going to happen if it travels very, very slowly? The ball falls out. So, but if it spins very, very fast, it stays inside. Of course, there is that critical speed between falling out and staying inside. And of course, much funnier to do it with water. I just want to show it does have water. What's this? What is that? How do you know? Where else could it be? Now you're in a splash zone, so. Of course, you should be worried every time when you take this course. Do you want me to spin it slower and slower? No? That's okay. All right. Probably wise decision. So we need to calculate that speed. Of course, we just have to choose which point you want to use. Is it the bottom or the top, the critical location? What do you think? Top, of course. At the bottom, actually, water gets compressed toward the bucket. So this is at the top. What forces are acting on the ball or on water? Of course, gravity. And what's second force? Is it tension, an actual force? Does string attached to water. Does it act on water? No. What does act on water? Bucket. And how do we call this force? Normal. That's a normal force. So that's the normal force. But the equations are exactly the same. So we know for the top location, this is what we should write. Now, see, when velocity getting, well, when we move it slower and slower and slower and slower, how does it affect gravity? It doesn't. So what does it affect? Normal force. If we move it slower and slower, hence the normal force also decreases in magnitude. Eventually, what's the smallest magnitude it might have? Zero. That's the smallest. The normal force is greater or equal to zero. It cannot be less than zero. So when normal force becomes zero, force of gravity becomes equal to mv squared over r. This is that critical speed we're looking for. When we move it faster than that speed, nothing bad is happening. But if we start moving it slower, that's it. Water or ball, anything start falling out. And turns out mass doesn't matter for that critical speed. It's getting canceled, and we just have to calculate this. V equals square root of g times r, 10, bless you, times a half of a meter, so square root of 5. Yeah, I should have made it 40 centimeters. That would have been square root of 4. So about 2.2 meters per second. But at the bottom of the trajectory, it experiences extra weight. Any questions? Well, we don't want to solve this problem. I just want to demonstrate it's solved. Yeah, I just want to demonstrate this experiment, what's happening. It's like a simple model of a roller coaster. If we don't have enough initial height, we don't travel fast enough to travel through. We just fall off the rail. Everything's dead. Everything's broken. Everybody's dead. But there is that critical height. If we start above that, even with friction, we can get through. And that's what every engineer who makes roller coasters needs to calculate. And in this situation, we should use a combination of law of conservation of mechanical energy because it's easier. MGH, initial potential energy, getting transferred into kinetic energy. But again, at which point should we look at the motion of this object? At the bottom or at the top? Which is critical? The top is critical. And if we consider exactly the same equation, Newton's second law, as we just did before, we get this. Same equation. At the top, normal force plus gravity equals ma. Exactly same equation. But we're now adding one more equation, which we've extensively studied. Law of conservation of mechanical energy. We neglect friction. That's why we use the law of conservation of mechanical energy. Initial gravitational potential energy here should be equal to, well, if we measure from zero potential energy here plus kinetic energy here. That's the law of conservation of mechanical energy. That's it. The rest is just some algebra. Turns out an ideal rail, no friction. This is also rotates, it's a ball. So in an ideal case, the initial height should be equal to about 2.5 radius of this loop. Done with vertical. Start about horizontal. Let's talk about horizontal motion. Where is it? Where is it? Oh, here. A horizontal motion. This device just helps to see at a horizontal motion a relatively long period of time. It's almost frictionless axle. So this ball spins horizontally. That's what we call horizontal circular motion. You do agree it's horizontally. You do agree it's circular. That's it. What do we do to analyze this motion? We apply exactly the same approach. Forces acting on it, gravity and tension. Well, geometrically a little bit harder because tension has a certain angle, but we've done it before. So we can do it again. I want to ask you this question. You just saw what was happening, and then there is a snapshot, a photograph. That's the instantaneous location of this very ball, which spins. And I want to ask you, this is question number 6 now. Right? Yeah. I want to ask you, what do you think about the direction of the acceleration? Why is it important? Well, because for a motion, for a circular motion, if we want to apply the Newton's second law, we have to see the acceleration. Otherwise, we may make a mistake. So here, again, it is useful to imagine 2 pictures of what's happening. This is actually what we call a side view. How would it look if you try to watch it from above? Because when you have a side view, you don't see the circle, you don't see the trajectory. And it always is helpful to see the trajectory, to see that circle. And for this situation, you can imagine that you look from above, that's your eye. And so pick your answer, remember it. So side view looks like this. We don't really see the circle. Well, we could imagine something like this. But technically what we see is a straight line. And that would have been force of gravity. That's supposed to be tension. Well, here technically we already know if this is the center of that circle, acceleration must point at it. But if we imagine that we look from above, it's even easier to see what's happening. From above, if our imagination is powerful enough, that's what we would see. Circular trajectory, a ball. That's the center, so that's supposed to be direction of acceleration. A top view is not very convenient in terms of forces because, again, gravity should be invisible for us. It should point away from us. And tension, how would we draw a tension? So that's why it's advisable to draw both views every time to see everything you may see. Now, that's the answer. I'm not going to ask this question for you, but think about it. It's the same. You see, I moved the weight, the ball, up and down. So it is the same system. And the same is the keyword. In both situations, this ball is the same. It's just if I move it higher, the radius, this string getting longer, the radius getting larger. If I move it lower, the radius getting smaller. But since it's the same ball, oops, it has the same mass, which means force of gravity acting on it will be the same. Force of tension in the string will be the same. So in both situations, tension will be the same. The radius will depend on what? On how fast it moves. And of course, we need to calculate. So this is a specific situation. All we need to do is just add forces, tension, gravity. How does acceleration point for this blue ball? So up, down, left, right. We have to show the center. And now with all good, acceleration must point toward the center of the circle. Plus m times a should be equal to tension plus gravity. Now, at this point, again, we have a choice to make. We can use components or we can use triangles. And since, again, I expect having a right triangle, I use triangles. So this is tension. No, this is MA. That should be equal to tension plus gravity. So hence my triangle should look like this. This arrow plus this arrow. The only mistake I can make is drawing this arrow, mg, too short or too long. If I draw it too short, it's always helpful to see what mistakes could be made. If I draw it too short, MA as a resultant should point like this. And that's wrong. It doesn't point to the center anymore. Wrong. All right, if you didn't succeed first time, try and try again. So I'm trying again. Yeah, I'm wrong again. Wrong again. Think. Okay. Let's concentrate. Stop. Whew. Now everything is absolutely correct. This is tension. This is force of gravity. This is m times a. This is the angle, wherever it is. So, for example, I can write mg over ma equals tangent of this angle. I can write tension equals square root of mg squared plus ma squared. In this particular problem, we also know the length. Why do we need it? Well, in this particular problem, since there's length, this geometrical triangle tells us how to relate length and the radius, this radius. A equals a centripetal should be equal to speed squared over the radius. This radius is related to the length. The length how? Well, it equals to hypotenuse times cosine of this angle. And that's it. If you use all the algebra, plug it in, you can, in this particular problem, calculate the speed. But of course, if you have a set of equations, you can solve those equations for any variable you may need to solve it for. You can solve it for tension, you can solve it for angle, depending on what you're given and what you're looking for. Have you been on a swing, on a carousel? You know now why this problem is very important. Now, if you drive, you know that friction, that's the force which makes you making a turn. If you evil person and you put some oil on the road, that's it. The car starts skidding away. Friction is important, and of course, the radius of a turn is related to how fast you move and related to the friction. And here, in this particular example, we know speed, we know the radius, and we need to calculate the coefficient of friction. Do we really care what we need to calculate at this point? Of course not, because any problem is not about what we're looking for. Every problem is about what's related to what. And then algebra can be solved for any variable. So, again, this is a photograph at certain angle. We need technically two views which would help us to visualize what's happening. The top view is just a circle. So this is a car. A snapshot, let's say it travels this way, it's instantaneous velocity. This is the center of a circle. So the acceleration is supposed to be directed toward the center of the circle. How do we draw normal and gravity? Well, actually, we can't clearly draw if we use top view. But on a side view, we can draw normal and gravity. That's still center of a circle. This is still the acceleration. And as we said, what is that force which is responsible for the existence, for the very existence of the acceleration? Friction. So we can draw a force of friction here. We can draw the force of friction here. Now, normal and gravity cancel each other out. And I should have used the opposite. Technically, everything which points to the left is negative for us. So I should write this equals this. But let's multiply by -1. That gives m a centripetal equals friction. Friction equals coefficient times normal. Normal equals mg. Mass getting cancelled. V squared over r equals coefficient times g. And now you can solve it for anything you need. In this particular problem, we are solving this for the coefficient, that critical. 72 miles, wrong number. What's wrong with that? Miles. So 72 miles. 1 mile is 1,600 meters. 1 hour is 3,600 seconds. That's supposed to be squared. We need to divide by the radius, which is 100 meters, and 10. And wherever it is, that's wherever it is. What would be happening if you would travel faster on the same surface? In that case, your radius would increase. That's it. Slower, yeah. If you travel slower, same surface means same friction. In that case, you would be making turn with a smaller radius. Now, Probably last problem for today. I've prepared the question. I will not ask you. We have only 10 minutes left. This is what a banked curve is. This is a Daytona race track, or there's a bike race tracks also angled. We know what to do. That's the question I wanted to ask you, so I'm not going to ask you. We know what to do. We have to draw a free body diagram. We have to draw it very accurately. All right, so let's draw the free body diagram very accurately. Again, if we look at this from a top view, that's what we see. And sometimes top view is good, sometimes not very good in terms of clarity. How should acceleration point at this particular instant? Well, it always points toward the center, and that means right here, right now, it points to the left. That's how we call this direction. And well, unfortunately, that's it. So the side view looks like this. It does look like an object on a ramp, but it is not an object on a ramp. Ramp and banked, different words, different things. What is different? On a ramp, an object slides down. Here, the car travels in a circle. Here, velocity directed like this. Here on this picture, we wouldn't see velocity. It aims away from us. But still, that is the center of the same circle. Still, acceleration points toward the center. Still, it means to the left. Now, there's gravity, always down. And there's one more force which is perpendicular to the surface. How do we call it? Normal force. Now, we got to say something about friction, and that's kind of tricky part. Friction, in general, a very, very tricky force. Of course, we need friction between wheels and road to make it move. But actually, after that, we don't need friction anymore. If it might travel just, if we make it move, it will travel, fall. If it travel by inertia, with constant speed. So technically, in this situation, we don't need friction. Friction might help, but we don't really need it. What force is responsible for centripetal acceleration now? You have to choose between gravity and normal. Can gravity be responsible for acceleration? No, because it's perpendicular. What's left? Normal. Normal force has two components. One component is horizontal. Let's call it x. Second component is vertical. And if we redraw our picture, this is what we would see. Actual force. The x component of the normal force, the y component of the normal force. What did we do? We replaced an actual force with its components. Now, but now if we look at this picture, it's very clear that gravity cancels only vertical component of the normal force. And centripetal acceleration times mass should be equal to the horizontal component of the normal force. Plus geometry, which tells us something about angles. Banked angle, yes, theta. That should be equal to this angle, theta. These are two horizontal lines crossed, so theta, geometry. In my triangle, for the normal force, this red dashed line supposed to represent the actual normal force. So if this is theta, that should be 90 minus theta, this should be theta. So now this is my triangle. Theta, actual normal force, Fy normal, Fx normal, and Fy normal over hypotenuse should be equal to cosine of this angle, which means the normal force, actual normal force, should be equal to Fy normal over cosine of this angle, which is mg divided by cosine. Pure geometry at this point. So I wanted to see the difference. This is how we calculate the normal force. This is how we calculate the normal force on a ramp. Yeah, that was an expression we've used before. And we cannot use this expression in this situation. This is how we should calculate the normal force if we need now. Different. But of course, at this point, all we have to write is just one more equation, this equation. Centripetal acceleration equals v squared over r. And if we multiply, well, okay. That's the picture. So mv squared over r should be equal to the x component of the normal force. That's it. The x component of the normal force, will be equal to normal force times sine of theta. Again, at this point, it is just a pure geometry. I'm going to copy a picture that is in actual normal force. The trickiest part sometimes for people is to relate this angle with this angle. This is an actual physical angle. That's how this track has been built up, and this is the geometry. Well, the solution, algebra, gives this answer. We can solve it for radius if we need if we know the speed in this situation. In this situation, we were looking for the speed. We know angle, we know radius. So we do algebra, solve it for the speed, and we're done. 43 meters per second. And we're done. Saturday begins now. Good morning. Just give me a second. I'm going to clear it up. You know what? So Professor Duffy is all set?
No.
What does he want?
The ball rolling down.
I brought it downstairs. He's all set. So no rush. We're just going to... But first, so I'm going to clean up. You can start, just put everything on different carts. I'm just going to raise, and you can dump water. Yes.
I won't be here next Wednesday. I'm going to court. So how should I make up my lab section?
I advise you to do it on Tuesday. Go to the Tuesday section.
Isn't the Wednesday the same as the Thursday though?
I need to see. I'm not sure. I need to see.
Okay.
Next week we have 2 labs.
Yeah.
Yes, you're right. No. Tuesday, Monday, Tuesday, Wednesday, Thursday. Yeah, you can go in a Thursday.
Could I also go? So like you have 11 to 2:30, or yeah.
On Thursday we only have 1 section.
No, for the Wednesday one, there's 11 to 2:30, and then there's like a 2:30 to 5:30.
You can, yeah.
Okay.
But
good.
you need to send me an email.
Okay.
This week.
Yes.
Can I get this question regraded because I